in the farthest dark beyond Neptune, across the giant planets, through drifting dust, restless atmospheres, and the changing face of the Sun. New observations are revealing a solar system that may not be as steady as it once seemed. Scientists are now watching subtle shifts in space, on distant worlds, and deep within solar activity itself, asking whether something larger is changing across our cosmic neighborhood. If this is the kind of deep space mystery that fascinates the mind, please like the video, subscribe to the channel, and join us as we follow the evidence inward, one world at a time. At the farthest known reach of the Sun's influence, space does not end, but it thins into a region where the solar system meets the wider galaxy. This distant boundary is shaped by a steady outward flow of charged particles from the Sun, known as the solar wind. This wind carries energy and magnetic structure across vast distances, expanding into a bubble that surrounds all the planets. The boundary of this bubble is not a solid edge, but a gradual transition where the outward pressure of the solar wind slows and is balanced by the faint material that drifts between the stars. Observations indicate that this boundary shifts over time, expanding and contracting in response to changes in solar activity. It remains uncertain whether these changes follow a simple repeating cycle or reflect deeper variations within the Sun. The region where the solar wind begins to slow is often described as a termination zone. Here, the outward motion of particles decreases as they encounter resistance from the interstellar medium, a sparse mixture of gas, dust, and magnetic fields that fills the space between stars. The particles in this region do not stop suddenly. Instead, they compress, heat slightly, and begin to behave in a more complex way, influenced by both the Sun and the galaxy beyond. Instruments carried by distant spacecraft have recorded changes in particle speed, density, and direction as they move through this region. These measurements show that the boundary is not smooth. It has folds, ripples, and variations that reflect both solar conditions and the structure of the interstellar environment. Beyond this slowing region lies a broader boundary where the Sun's influence weakens further. The solar wind no longer dominates motion here. Instead, the particles from the Sun and the particles from interstellar space mix and interact. Magnetic fields carried outward from the Sun begin to bend and align with the broader magnetic field of the galaxy. This interaction forms a complex interface where energy is exchanged and particles change direction. Observations from spacecraft that have crossed into this region indicate a clear shift in the origin of particles. The number of particles from outside the solar system increases, while those from the Sun decrease. This transition marks a gradual crossing from one environment to another rather than a sharp border. The shape of this outer boundary is not perfectly round. It is influenced by the motion of the solar system through the galaxy and by the pressure of the interstellar medium. As the Sun moves, it creates a subtle compression at the front and a longer, trailing extension behind. This structure resembles a flowing form, stretched and shaped by motion. Measurements suggest that the boundary is asymmetric, with distances varying depending on direction. Some regions lie closer to the Sun, while others extend farther outward. These differences reflect the uneven nature of the interstellar environment and the changing strength of the solar wind over time. Changes in solar activity play a central role in shaping this distant region. The Sun does not emit a constant flow of particles. Its activity rises and falls over a cycle that lasts about 11 years, marked by variations in magnetic activity and surface features. During periods of higher activity, the solar wind becomes stronger and more dynamic. It carries more energy outward, pushing the boundary farther into interstellar space. During quieter periods, the wind weakens, allowing the boundary to contract slightly. Observations indicate that these changes propagate slowly through the solar system, taking years to reach the outermost regions. As a result, the boundary reflects not only current solar conditions, but also the history of solar activity over time. Recent measurements suggest that this boundary may be changing in ways that extend beyond the expected cycle. Instruments have detected variations in the density and energy of particles that do not align perfectly with the timing of solar activity. In some regions, the boundary appears to shift more rapidly than models predict. In others, the structure of the boundary shows unexpected complexity, with layers and gradients that are not fully explained. It remains uncertain whether these observations indicate a longer-term shift in solar behavior or changes in the surrounding interstellar medium. Both possibilities are consistent with known physical processes, and further observation is needed to distinguish between them. The interstellar medium itself is not uniform. It contains regions of slightly higher density, as well as variations in temperature and magnetic field strength. As the solar system moves through this medium, it encounters different conditions. These variations can alter the shape and position of the boundary. For example, a region of denser interstellar material can compress the boundary, bringing it closer to the Sun. A region with stronger magnetic fields can change the way solar and interstellar particles interact, creating new patterns of motion. Observations indicate that the solar system may currently be passing through a region of local interstellar cloud material, which has its own distinct properties. It remains uncertain how long this passage will last, or how strongly it will influence the boundary over time. Cosmic rays, which are high-energy particles that originate beyond the solar system, provide another way to study this distant region. As these particles travel inward, they are affected by the solar wind and its magnetic field. A stronger solar wind tends to deflect more cosmic rays, reducing their number closer to the Sun. A weaker solar wind allows more cosmic rays to penetrate deeper into the solar system. Measurements of cosmic ray intensity at different distances show variations that correspond to changes in solar activity and boundary conditions. In recent years, some instruments have recorded higher levels of cosmic rays than expected, suggesting that the shielding effect of the solar wind may have weakened. It remains uncertain whether this is part of a temporary fluctuation or a longer-term trend. The distant boundary of the solar system, though far removed from the planets, plays a role in shaping conditions throughout the system. It acts as a filter, moderating the flow of interstellar particles and radiation that enter the region dominated by the Sun. Changes at this boundary can influence the environment in which planets, moons, and smaller bodies exist, while the effects are subtle and spread over long timescales. They are part of a connected system in which distant and near regions are linked by flows of energy and matter. The evidence gathered from spacecraft and remote measurements shows a region that is dynamic rather than fixed. The boundary shifts, responds, and adapts to both internal solar changes and external galactic conditions. Observations indicate patterns of variation, but they also reveal uncertainties that remain unresolved. It is clear that the outermost region of the solar system is not static. It evolves over time, shaped by forces that extend far beyond the Sun itself. This evolving boundary forms the outer layer of a system that continues inward, where each region carries its own signs of motion and change. Beyond Neptune, the solar system opens into a wide and cold region filled with bodies that are small beside planets, yet immense when measured against ordinary mountains or seas. These distant objects move through darkness so deep that sunlight arrives as a weak and steady glow, enough to illuminate surfaces faintly, but too little to bring warmth in any familiar sense. Here, Water exists not as flowing liquid but as hard ice. Methane, nitrogen, and carbon monoxide also freeze into solid form. These materials rest on ancient surfaces that preserve the record of low temperatures, slow collisions, and long exposure to radiation. This region is often called the Kuiper Belt, though its full structure includes Kama belts, scattered paths, and isolated bodies moving on stretched and tilted orbits. Observations indicate that these objects are leftovers from the early solar system, material that never gathered into a planet because the outward pull of distance and the inward influence of giant planets prevent such a simple outcome. The bodies in this region differ in size, shape, and brightness. Some are small fragments, dark and irregular, turning slowly as they travel around the Sun over hundreds of years. Others are large enough for their own gravity to draw them into rounded forms. Pluto is one of the best known among them, but it is only one member of a wider population that includes Eris, Makemake, Haumea, and many other icy worlds. Their surfaces are not all the same. Some appear reddish, marked by complex carbon-rich material altered by radiation. Some are brighter, carrying fresh frost that reflects the weak sunlight. Some show patches of exposed water ice, while others hold more volatile ices, substances that can slowly shift or escape when conditions change. These differences suggest that even in this cold and distant realm, surface conditions do not remain perfectly fixed. The motion of these objects reveals that this outer region is not a quiet shell arranged in neat order. Many bodies follow orbits shaped by Neptune's gravity. Some move in resonances, which are repeating orbital patterns in which one body circles the Sun a set number of times while Neptune completes another set number. Pluto follows one of the most stable of these patterns. Such motion protects certain objects from close encounters, but it also shows that the history of the outer solar system includes movement and rearrangement. Models of planetary formation indicate that the giant planets likely shift their positions early in solar system history. As they move, they scatter smaller, icy bodies outward and trap some into repeating paths. The distant region that appears still in the present carries signs of a more active past. Yet the evidence for change is not limited to ancient history. Observations over recent decades suggest that some of these distant bodies continue to evolve in small but measurable ways. Their brightness changes with season, rotation, and surface frost. Pluto provides the clearest example because it has been studied closely from Earth and by spacecraft. Its thin atmosphere, formed when surface nitrogen ice turns directly into gas under weak sunlight, expands and contracts as its long seasons progress. Since Pluto takes more than 200 Earth years to complete one orbit, its seasons unfold slowly, yet they are real. Measurements indicate that its atmosphere has changed over time, reflecting the delicate balance between sunlight, ice, and escape to space. Even at such great distance, the Sun still drives motion, though that motion is patient and restrained. Other large icy bodies also show signs of unusual histories and changing surfaces. Haumea, with its elongated shape and rapid rotation, appears to be the outcome of a violent collision in the past. It carries water ice on its surface and is accompanied by smaller related bodies that may be fragments from that event. Makemake and Eris display bright frosts and highly reflective surfaces, suggesting the presence of frozen volatile material. Observations indicate that radiation from the Sun and from cosmic rays alters the uppermost layers of these surfaces over time, darkening some regions and reddening others. Impacts from smaller bodies can excavate fresher ice below. In this way, even a frozen surface that appears ancient is slowly renewed and altered by exposure, collision, and orbital change. Farther still are bodies on more scattered paths, some sent outward long ago by the gravity of Neptune. These objects travel on stretched orbits that carry them far from the Sun and then return them inward again, though still beyond Neptune for most of their paths. Their existence suggests a region that grades outward into even more distant reservoirs of icy bodies. Some of these scattered worlds appear detached from the main influence of Neptune, moving on paths that are difficult to explain with present planetary positions alone. Observations indicate that the early solar system may have passed through a stage of strong gravitational reshaping, perhaps involving migration of the giant planets, interactions with passing stars in the Sun's birth cluster, or the collective influence of many icy bodies. It remains uncertain which combination of processes produces every orbit now observed. But the outer structure clearly preserves a memory of rearrangement. The surfaces of these distant objects are shaped by more than sunlight alone. They endure a steady rain of energetic particles. Cosmic rays and ultraviolet light break apart simple molecules in the surface ice and allow new compounds to form. Over long periods, this chemistry can produce dark and reddish material that blankets the ground in a thin processed layer. This means that a distant body can change even in apparent stillness. Its color may shift, its reflectivity may fade. A fresh impact may expose brighter ice beneath. A slight change in solar heating along an eccentric orbit may move frost from one region to another. None of these processes is fast, but together they show that distance does not mean complete inactivity. New evidence also comes from the simple increase in what can now be seen. Larger telescopes, improved detectors, and careful long-term surveys continue to reveal more bodies in this outer population. With each new orbit measured, patterns become clearer and old assumptions are tested. Astronomers now understand that the region beyond Neptune is more structured than once thought. It contains families of objects, resonant groups, scattered populations, and isolated extremes. The distribution of their sizes and orbits suggests that the outer solar system has not been shaped by one quiet process alone. It is the result of growth, collision, migration, and continued exposure to a changing space environment. In this remote region, change is not dramatic in the ordinary sense. It is expressed in slight shifts of light, in frost that advances and recedes across centuries, in thin atmospheres that appear and thin again, in colors altered by radiation, and in orbital patterns that preserve old disturbances. The evidence suggests that the distant icy bodies of the solar system are not frozen only in temperature. They are also frozen archives, holding traces of motion and transformation across immense spans of time. Their surfaces and paths show that the outer solar system remains a place where history is still visible and where subtle change continues under the weakest light of the sun. Beyond the belt of icy bodies and scattered worlds, this solar system gathers itself into larger forms. The giant planets hold wide domains of gas, ice, storms, rings, moons, and magnetic fields. They are not fixed monuments set in darkness. They are active systems, changing on timescales that range from hours to centuries. New evidence suggests that these outer planets, once thought of mainly as slow and distant, are revealing fresh signs of motion and adjustment. Their clouds shift. Their winds vary. Their rings respond to collisions and gravity. Their magnetic fields interact with the solar wind in ways that alter surrounding space. Each giant planet forms a regional system of its own. Yet together they show that the outer solar system is not quiet. It remains in motion, shaped by energy from within and from the Sun. Jupiter stands as the largest of these worlds, a planet made mostly of hydrogen and helium, with no solid surface in the familiar sense. Its visible form is an atmosphere of layered clouds, banded by powerful winds that circle the planet in alternating directions. These bands, pale and dark, are not purely decorative. They reveal different levels of rising and sinking gas, shaped by heat escaping from deep within the planet and by the rapid rotation of Jupiter itself. Observations over many years show that these cloud bands do not remain exactly the same. Their colours fade and strengthen, their boundaries shift. Some belts grow darker, then later become pale again. These changes suggest that material from deeper levels rises upward, and that chemical compounds in the upper atmosphere are constantly being rearranged. Within Jupiter's cloud system, storms form and persist with remarkable scale. The Great Red Spot is the most famous, a long-lived rotating storm larger than Earth for much of recorded observation. Yet even this great feature changes. Measurements indicate that it has shrunk over time, becoming more compact than it appeared in older observations. Its colour also varies, sometimes deepening, sometimes growing more muted. Smaller storms merge, shear apart, or vanish. Bright plumes rise and spread. Lightning flashes within turbulent cloud towers. These changes do not mean instability in the sense of collapse. They show that Jupiter's atmosphere is alive with circulation, driven by heat from below and by the planet's swift spin. New evidence from spacecraft and telescopes continues to refine the picture, showing that storm systems connect to deeper layers more strongly than once assumed. Jupiter also carries a vast magnetic field, produced by electrical currents deep within the planet where hydrogen is compressed into an unusual conducting state. This magnetic field extends far into space and traps charged particles in broad belts of radiation. The field is not perfectly simple. It is uneven, tilted, and marked by local strengths and weaknesses. Observations from recent missions indicate that the magnetic structure is more complex near the planet than earlier models suggested. As Jupiter rotates, this field sweeps through surrounding space, interacting with the solar wind and with material released by its moon, Io. Io is intensely volcanic, sending sulfur and oxygen into space, where these atoms become ionized, meaning they lose or gain electrons and become electrically charged. This material feeds a torus, a broad donut-shaped ring of plasma around Jupiter. The result is a giant magnetosphere, a magnetic region, that changes as solar pressure varies and as the supply of particles from Io rises and falls. Saturn appears calmer at first glance, wrapped in softer colours and more even bands. But it too is a changing world. Its atmosphere carries strong winds and long-lived storms. At times, large bright eruptions rise through the cloud layers and spread around the planet, disturbing the surrounding atmosphere for months. Near the North Pole, Saturn holds a remarkable six-sided wave pattern, often called a hexagon, which persists while smaller cloud forms within and around it continue to shift. Observations indicate that Saturn's atmosphere also changes with season. Because Saturn takes nearly 30 Earth years to orbit the Sun, each season lasts for more than 7 Earth years. As sunlight angles change over time, the brightness and chemistry of haze layers alter, changing the appearance of the planet's hemispheres. Saturn's rings provide some of the clearest evidence that change remains visible in the outer solar system. These rings are composed mostly of water ice, broken into particles that range from tiny grains to large blocks. They circle in a thin, broad system shaped by gravity, collisions, and the pull of nearby moons. The rings are not solid structures. They are dynamic, with waves, gaps, braided patterns, and temporary disturbances. Small moons shepherd some ring edges, keeping particles confined. Passing objects can leave ripples that travel outward through the ring system over time. Observations indicate that meteoroid impacts contribute dust and gradually darken ring material. Some evidence suggests that ring particles also fall slowly into Saturn's upper atmosphere in a process often described as ring rain. It remains uncertain how old the rings are in their present form, but it is clear that they are evolving. The moons of the giant planets add another layer of change. Around Jupiter, Europa carries a surface of fractured ice that likely covers a global ocean beneath. Ganymede holds its own magnetic field, unique among moons, and Callisto preserves a more ancient battered surface. Around Saturn, Enceladus releases plumes of water-rich material from fractures near its south pole, feeding one of Saturn's faint rings and revealing ongoing activity within a small frozen body. Titan, Saturn's largest moon, carries a dense atmosphere rich in nitrogen and methane, with clouds, rain, rivers, and seas of liquid hydrocarbons. Seasonal change alters Titan's clouds and haze. These moons show that the giant planet systems are not only shaped by the planets themselves, they are full miniature worlds with internal heat, subsurface oceans, chemical cycles, and active surfaces. Uranus and Neptune lie farther outward, colder and dimmer, yet they are not inactive. Uranus is unusual because it rotates tipped on its side, likely due to a major collision early in its history. This extreme tilt produces unusual seasons. As Uranus moves around the Sun, one pole then the other points more directly towards sunlight for long intervals. Its atmosphere, once thought nearly featureless, has revealed storms, bright cloud structures, and shifting haze when observed carefully with improved instruments. Neptune, farther still, shows some of the fastest winds in the solar system. Dark storms appear and disappear in its atmosphere, accompanied by bright methane ice clouds at high altitude. These storms do not persist in exactly the same way as Jupiter's Great Red Spot. They form, drift, weaken, and are replaced. Observations indicate that Neptune's atmospheric brightness has varied in recent years, showing that even this remote planet responds to internal dynamics and solar illumination. The magnetic fields of Uranus and Neptune are also unusual. Unlike the more centered magnetic structures of Earth, Jupiter, and to a lesser degree Saturn, the fields of these ice giants are strongly tilted and offset from the planetary centers. This creates changing magnetic geometry as each planet rotates, producing complex interactions with the solar wind. The surrounding charged particle environments expand and compress as solar conditions change. These interactions remind observers that the giant planets are linked to the wider solar system through flows of plasma and magnetic energy. Taken together, the giant planets show a region of the solar system that is broad but not still. Cloud belts shift, storms evolve, rings ripple, moons vent material, and magnetic fields reshape surrounding space. New evidence does not suggest that these worlds have recently become active. Rather, it shows more clearly that activity has been present all along, visible now through longer observation and better instruments. The outer giant planets remain a theatre of slow but persistent change, where large structures endure while details continue to move within them. From the far icy reservoirs and the realms of giant planets, some bodies begin a long inward journey. They do not travel in crowds or in stable belts alone. They arrive as wanderers on stretched paths, carrying frozen material from distant cold into regions where sunlight grows steadily stronger. These are comets, bodies made largely of ice, dust, and rocky grains, preserved for immense spans of time in the outer solar system and then altered as they approach the Sun. Around them moves a finer population of drifting dust, made from collisions, from comet activity, and from the constant breakdown of larger bodies. Together, comets and dust form a moving link between the cold outer reaches and the warmer inner system. They carry ancient matter inward, and as they do, they begin to change in ways that can be observed directly. A comet in the far outer solar system is a dark object. Its surface is often coated in material altered by radiation, which can reduce reflectivity and hide the brighter ices beneath. In this distant state, the comet may appear inactive, little more than a dim nucleus, which is the solid central body. It can remain in such a condition for long intervals, moving slowly through regions where sunlight is too weak to drive visible change. Yet this quiet appearance does not last once the comet approaches the Sun. As light and heat increase, the most volatile frozen substances begin to transform directly from solid into gas. This process is known as sublimation. It does not require melting. Instead, the ice changes state at the surface or just below it, and the gas then escapes through pores, cracks, or exposed patches. As gas escapes, it pulls dust with it. A cloud begins to form around the nucleus. This cloud is called the coma. It can grow to enormous size, though the central body remains relatively small. The coma is thin, but in sunlight it becomes visible because gas molecules and dust grains scatter and reflect light. Under the pressure of sunlight and the flow of the solar wind, material in the coma begins to spread outward into tails. These tails do not trail directly behind the comet like the wake of a boat in water. One tail, made of ionized gas, points more directly away from the Sun because the solar wind carries the charged particles outward. Another tail, made mostly of dust, curves more gently because dust grains respond mainly to sunlight and to the comet's forward motion. In this way, a comet reveals its interaction with the inner solar system not only through its own activity, but through the form and direction of the material that leaves it. This activity is not always smooth. Some comets brighten suddenly. Jets erupt from localized areas where sunlight reaches fresh volatile ice. As the comet rotates, these active regions swing in and out of illumination, causing the pattern of escaping gas and dust to vary over hours or days. Surface layers can crack under thermal stress, which is stress produced by repeated heating and cooling. Dust can build into fragile crusts that later break apart, briefly exposing more active ice below. Observations indicate that many comets lose material unevenly, becoming shaped by their own activity. Some develop pits, steep scarps, and layered terrains. Spacecraft images of comet nuclei show surfaces that are not smooth snowballs, but complex bodies with cliffs, plains, broken edges, and deposits of fallen dust. The old picture of a comet as a simple frozen lump has given way to a more detailed view of a changing small world. The closer a comet comes to the Sun, the stronger these processes become. Water ice, which requires more heating than some other frozen substances, becomes active in the inner solar system. Gas flow can increase. Dust production can thicken the coma and widen the tail. In some cases, a comet approaches so close to the Sun that intense heating drives violent mass loss. Fragments can break away. Some comets survive repeated passages, adjusting slowly as surface layers are stripped and fresh regions are revealed. Others split or disintegrate entirely. Observations indicate that such breakups are not rare. They are a normal part of comet evolution. A comet is not only a messenger from the outer solar system, it is also a body in the process of being changed. depleted, and in some cases destroyed by the environment into which it travels. The dust released by comets does not vanish once a bright tail fades from view. Much of it continues to orbit the Sun, joining a broader cloud of fine particles spread through interplanetary space. Some of this dust comes from comet activity. Some comes from collisions between asteroids and from impacts on small bodies. The inner solar system therefore contains a diffuse haze of particles that reflect sunlight. Seen from dark places on Earth, this haze can appear as the zodiacal light, a faint glow along the plane of the solar system. Though delicate in appearance, this dust cloud is evidence of constant renewal. Individual grains do not remain forever in the same orbit. Sunlight exerts a gentle but continuous force on them, causing gradual drift. Collisions grind larger particles into smaller ones. Some grains spiral inward toward the Sun. Others are pushed outward or destroyed. The presence of the dust cloud shows that the solar system contains ongoing transport. Not merely preserved debris, dust grains also carry information about change. Their size, composition, and distribution reveal where they come from and how long they endure. Measurements from spacecraft and from telescopes indicate that different regions contain different particle populations. Fresh comet dust may be rich in primitive material, including silicates and carbon-bearing compounds formed early in solar system history. Dust from asteroidal collisions can differ in texture and thermal behavior. As grains are exposed to sunlight and charged particles, they alter chemically and physically. Some darken, some fracture, some lose volatile coatings. Even the smallest particles participate in the story of a changing solar system because they move, respond, and decay under the influence of radiation and gravity. Meteor showers on Earth provide a more immediate sign of this connection. When Earth crosses a stream of dust left behind by a comet, tiny particles enter the atmosphere at high speed and burn through friction with the air, producing brief streaks of light. These events are not random. They are the visible result of old comet passages, preserved as trails of debris along an orbit. In this way, the inward motion of distant comet material can later appear in the sky of an inner planet. The process links large timescales and small moments. A fragment released long ago from an icy nucleus far from the Sun can become a grain that briefly glows in Earth's atmosphere centuries later. New evidence from modern missions and long observation suggests that comets are more structurally complex and more active in detail than once assumed. Their nuclei contain layered deposits, uneven mixtures of ice and dust, and regions with very different responses to heating. Their activity can begin farther from the Sun for some volatile substances and then shift as different ices take over closer in. Dust studies show that interplanetary material is constantly replenished and redistributed. Nothing in this moving population remains entirely at rest. Matter from the outer solar system enters warmer space, sheds gas and dust, changes shape, and leaves behind trails that continue to circle the Sun. In this region of the story, change is carried inward by motion itself. Comets do not simply arrive. They react. Dust does not merely drift. It records collisions, erosion, and transport across wide distances. Together they show that the solar system is connected by streams of material that move from cold to warmth, from darkness to light, and from hidden storage to visible transformation. The evidence suggests not a system of isolated zones, but a continuous exchange in which ancient frozen matter begins, slowly and visibly, to change. Between the broad paths of Jupiter and Mars lies a region once imagined as the remains of a broken planet. That older picture has largely given way to a quieter and more accurate understanding. The asteroid belt is not the rubble of a lost world. It is a population of bodies that never became a planet at all. In the early solar system, material in this region begins to gather, collide, and grow. But the strong gravitational influence of Jupiter stirs the area too much for stable planetary assembly to continue. Instead of one large world, many smaller bodies remain. Some are rocky, some contain metal, some preserve water-rich minerals that point to an earlier interaction with liquid water inside their parent bodies. Taken together, they form a zone of incomplete formation, one that still changes under sunlight, impact, and rotation. From a distance, the asteroid belt is sometimes imagined as densely crowded. In reality, it is vast, and the bodies within it are separated by large distances. Yet this wide spacing does not mean inactivity. Over long spans of time, collisions occur. Some are gentle enough to shatter a surface and scatter fragments. Some are energetic enough to break apart an entire body. These impacts produce families of asteroids that share similar orbits and likely come from a common parent. By tracing orbital similarities and surface properties, astronomers identify these family groups and reconstruct past breakups. The belt therefore preserves a visible record of collision. It is not a still museum of untouched objects. It is a region where bodies strike, fracture, and slowly spread debris through orbital space. The largest asteroid, Ceres, differs from many of its neighbours. It is round under its own gravity and is classified as a dwarf planet. Its surface includes salts, clays, and signs of water-rich material. Bright deposits in some craters suggest that briny liquid, meaning water containing dissolved salts, once reaches or approaches the surface and then leaves reflective minerals behind as the water disappears. Observations indicate that Ceres is not merely a dry rock. It holds a more complex internal history, with ice, hydrated minerals, and perhaps pockets of muddy or salty material that moved slowly through its interior in the past. This does not imply oceans like those suspected beneath the ice shells of some outer moons, but it does show that even in the asteroid belt, some bodies experience chemical and thermal evolution. A small world can change from within as well as from outside. Vesta presents a different history. It is smaller than Ceres, but still large enough to have undergone internal heating early in solar system history. Evidence suggests that Vesta differentiates, meaning that its interior separates into layers, with denser material sinking inward and lighter rock remaining above. Its surface carries enormous impact basins near one pole, scars left by collisions powerful enough to excavate deep material and send fragments into space. Some meteorites found on Earth are linked to Vesta, allowing laboratory study of material from this differentiated body. In this way, the asteroid belt is not a collection of one kind of object. It includes bodies that remain primitive and bodies that change internally, melt partially, separate into layers, and later suffer major impacts that expose their deeper structure. Smaller asteroids across the belt show many forms. Some are solid monolithic objects, while others appear to be rubble piles, loose collections of broken material held together mainly by gravity. A rubble pile asteroid can form after a collision shatters a parent body, and the fragments later drift back together. Such a structure is weak in a mechanical sense. It can be reshaped by later impacts, by close planetary encounters, or even by the gentle but continuous force of sunlight. This force is subtle, yet over long periods it matters. When sunlight warms an asteroid and the surface later re-radiates that energy as heat, the outgoing radiation can produce a tiny push. This effect, known in astronomy as the Yarkovsky effect, slowly changes the orbit of small asteroids. It is a small force acting over immense time, enough to move objects gradually inward or outward, and to deliver some of them into resonances that alter their paths more dramatically. Rotation adds another layer of change. Sunlight can not only shift an asteroid's orbit, it can also change how quickly the body spins, especially when the object has an uneven shape. Over time, some asteroids spin faster. If a loosely bound body rotates too quickly, surface material may slide, migrate, or even drift away into space. Observations of some small asteroids show equatorial ridges, flattened shapes, and companion moonlets that may form when spun-off material reaccumulates nearby. These are not sudden transformations on human timescales in most cases, but they are real physical processes now seen clearly through radar studies, spacecraft visits, and repeated telescopic observation. The belt is therefore active in a quiet way, with light itself helping reshape small worlds. Surface change is also constant. Without thick atmospheres or flowing water, asteroid surfaces are exposed directly to the environment of space. Micrometeoroid impacts strike them repeatedly. Charged particles from the sun and cosmic rays alter the uppermost grains. Over time, this exposure changes the optical properties of the surface, often darkening or reddening it in a process called space weathering. A fresh impact can expose brighter material below. A landslide on a rapidly rotating body can reveal less weathered rock. The surface seen through a telescope is therefore not only a clue to composition, it is also a record of age, disturbance, and exposure. Two asteroids made of similar material can look different because one surface is fresher and the other has been altered for longer. The asteroid belt also acts as a source region for bodies that later move inward. Orbital resonances with Jupiter and Mars create unstable zones in the belt. When small asteroids drift into these zones through collisions or sunlight-driven motion, their orbits can change significantly. Some are sent onto paths that cross the inner planets. In this way, the belt is connected to the population of the near-Earth asteroids and to the history of impacts on terrestrial worlds. It is not sealed off from the rest of the solar system. It feeds material outward in the form of dust and inward in the form of migrating rocky bodies. This ongoing transfer means that the belt participates directly in the wider circulation of matter. New evidence from spacecraft missions has deepened this picture. Close images of asteroids reveal boulders, regolith, meaning loose surface debris, fractured ridges, and signs of surface motion. Sample return missions bring back grains that show the chemistry of primitive solar system material and the effect of alteration by water in some parent bodies. Long-term surveys continue to detect new small asteroids, family relationships, and changes in brightness caused by rotation or by impact events. Occasionally, an asteroid displays comet-like behavior, releasing dust through impact, spin-driven shedding, or in rare cases sublimation of hidden ice. Such objects blur older categories and show that small bodies do not always fit into neat divisions. The asteroid belt in sunlight is a region of fragments, but not of silence. Its bodies turn, drift, collide, weather, and sometimes expose their deeper past. Some preserve the earliest building material of planets. Some record internal heating and separation into layers. Some are pushed by nothing more than uneven warmth from the sun. New evidence suggests not that the belt has suddenly awakened, but that its continuous small changes are now more clearly visible. The region between Mars and Jupiter remains a zone of unfinished formation and ongoing modification, where broken stones and ancient light continue to shape one another. Mars appears as a small red world set between the crowded belt of asteroids and the more familiar orbit of Earth. From a distance, it seems quiet, dry, and almost unchanged, a planet whose age is written in dust and stone. Yet closer observation shows a more active and responsive environment than that still image suggests. Mars has a thin atmosphere, weak compared with Earth's, but still capable of moving dust across continents, building clouds, changing with the seasons, and slowly exchanging material with the surface below. Ice lies at the poles and beneath the ground. Winds rise and fall, frost forms and retreats. The planet loses part of its upper atmosphere to space. These changes do not turn Mars into a warm or wet world in the present age, but they show that it remains a place where environment and surface continue to affect one another. The thin air of Mars is made mostly of carbon dioxide, with smaller amounts of nitrogen and argon. Surface pressure is low, far lower than on Earth, and this low pressure changes the behavior of cold, frost, and dust. Water is not stable as liquid over most of the surface today. Ice can exist, and water vapor can move through the air in small amounts, but long-lasting surface liquid is not supported under ordinary present conditions. Carbon dioxide, however, moves through a seasonal cycle that is one of the most important processes in the Martian atmosphere. During winter at each pole, temperatures fall so low that carbon dioxide freezes directly from the air onto the ground, forming seasonal polar frost. When spring returns, this frozen carbon dioxide changes back into gas and re-enters the atmosphere. Because so much of the atmosphere participates in this cycle, the pressure of the entire planet rises and falls through the year. This seasonal breathing of the atmosphere influences winds across Mars. As gas freezes and later returns to the air, pressure patterns shift. These shifts help drive circulation from one hemisphere to the other. The result is a changing system of winds that lifts fine dust and carries it over wide distances. Dust is one of the defining features of Mars. The planet's surface contains abundant fine red particles rich in iron oxides, minerals that have reacted with oxygen and give Mars its familiar color. Because the air is thin, strong winds are needed to move larger sand grains, but very fine dust can be raised more easily. Local whirlwinds, broad regional storms, and at times near-global dust events show that the atmosphere, though slight, is still strong enough to reshape the planet's surface appearance. Dust storms on Mars can begin in relatively small areas and then spread. Some remain local, some grow to regional size. In certain years, conditions favor much broader expansion, and dust rises high enough to veil large parts of the planet. When this happens, sunlight reaching the ground is reduced, while the suspended dust warms parts of the atmosphere above. This changes circulation further and can prolong the event. Observations indicate that global or nearly global dust storms do not occur every Martian year, but they are a recurring part of the planet's climate. Their timing and growth depend on season, sunlight, and atmospheric conditions. It remains uncertain why some years support especially large storms while others do not. Though the broad physical ingredients are understood, these storms are among the clearest signs that Mars remains environmentally active in the present. Clouds also form in the thin Martian sky. Water ice clouds appear in colder regions and at certain seasons, especially near volcanoes, over canyons, and in the morning sky, carbon dioxide clouds can form at higher altitudes where temperatures are extremely low. These clouds are delicate compared with the dense weather systems of Earth, but they show that Mars has an atmosphere capable of phase changes, transport, and structure. Frost forms on the ground in cold periods and disappears when sunlight returns. Haze varies with dust content and season. The sky itself changes color and clarity depending on how much dust is suspended in the air. Mars is not meteorologically empty. It has a reduced but still functioning climate system. At the poles, the seasonal rhythm becomes more visible. Mars has permanent polar caps made largely of water ice, covered seasonally by carbon dioxide frost. In winter, the caps spread outward as carbon dioxide freezes. In spring, sunlight returns and this seasonal layer begins to vanish. The process is not always gentle. In some places, sunlight penetrates translucent carbon dioxide ice, warming the darker ground below. Gas then builds underneath and escapes suddenly through weak points, carrying dark dust upward and outward. This creates striking fan-shaped deposits on the surface. Such features show direct interaction between sunlight, seasonal ice, gas flow, and loose material. Even in the coldest regions, the surface responds dynamically to changing light. Beneath the surface, Mars stores more ice than the bare ground first suggests. Radar and thermal studies indicate widespread ground ice in higher latitudes and buried deposits in other regions. Some slopes show recurring changes in brightness, though many such features are now understood to result from dry flows of dust and sand rather than present liquid water. The stronger evidence points to a planet where ice is stable below the surface in many places, and where that ice can affect soil strength, landscape shape, and long-term climate response. In earlier periods of Martian history, liquid water clearly does flow on the surface. River valleys, delta deposits, lake beds, and minerals formed in water all preserve that record. In the present age, the story is different. Water remains important, but mostly as ice, vapor, and chemically bound material, not as persistent flowing rivers. Mars also continues to lose atmosphere to space. Unlike Earth, it lacks a strong global magnetic field today. Without that broad magnetic shield, the upper atmosphere is more directly exposed to the solar wind, the stream of charged particles from the Sun. This interaction can strip away atmospheric particles over time. Measurements from orbiting missions show that the loss continues in the present and can increase during periods of stronger solar activity. This escape is not rapid enough to empty the atmosphere on human timescales, but over geological time it matters. It helps explain how Mars changes from a planet that once supports more surface water to the colder, drier world seen now. The process links the atmosphere of Mars to the wider solar system environment, showing that solar change can shape planetary evolution. Surface features on Mars also record ongoing movement. Sand dunes migrate slowly under the action of wind. Dust devils leave dark tracks by clearing brighter dust from the ground. Frost-related cracking, slope failures, and the creeping motion of loose material continue to alter the landscape. Repeated imaging of the same places over years reveals that Mars is not geologically dead in every sense. Large-scale volcanism is not active at the level clearly seen on worlds like Io, and plate tectonics in the Earth-like sense is absent, yet the surface remains responsive. Small changes accumulate across seasons and years. New evidence suggests that Mars is best understood not as a frozen remnant of a lost past alone, but as a planet still engaged in slow environmental exchange. Its thin air moves dust, its poles advance and retreat with the seasons, its upper atmosphere leaks particles to space, and its buried ice preserves a link between present conditions and ancient climates. The changes are restrained, often subtle, and governed by cold and scarcity, yet they are real. Mars remains a dry and shifting planet, where the traces of deep history are joined by the steady work of an atmosphere that still breathes, however faintly, under the light of the sun. Earth appears from afar as a bright and active sphere, layered with cloud, ocean, land, and a thin atmosphere that scatters sunlight into blue. Within the solar system, it is one planet among others, moving on a stable path around the Sun while turning steadily on its axis. Its familiarity can make it seem separate from the wider system, yet from a broader view it is fully immersed in solar influence. Light from the Sun drives weather and climate. Charged particles from the Sun press against Earth's magnetic field. Dust from space enters its atmosphere. Gravitational interactions with the Moon shape tides and help steady the planet's axial tilt over long timescales. Earth is not only a homeworld with its own internal systems, it is also a participant in the changing environment of the solar system, responding in ways that are sometimes immediate and sometimes so gradual that only careful observation reveals them. The atmosphere is the most visible sign of Earth's activity from space. It is thin relative to the size of the planet, yet deep enough to sustain complex circulation, clouds, and a strong greenhouse effect that keeps surface temperatures within the range needed for liquid water. Most of the atmosphere is nitrogen and oxygen, with smaller amounts of argon, water vapor, carbon dioxide, and trace gases. Sunlight warms the surface and lower air unevenly, more strongly at the equator than at the poles, more strongly by day than by night, and differently over land and ocean. These contrasts drive circulation. Air rises, cools, sinks, and flows. Water evaporates, condenses, and falls as rain or snow. From a solar system perspective, this active atmosphere is one way Earth responds to its position near the Sun. The amount of sunlight it receives is stable on short timescales, but the exact distribution changes with season because Earth's rotational axis is tilted. This tilt, combined with Earth's yearly motion around the Sun, creates the seasonal cycle. Each hemisphere leans toward or away from sunlight at different times of the year. Temperatures, storm tracks, plant growth, snow cover, and sea ice all respond. These seasonal changes are not signs of instability. They are part of the regular pattern of a tilted rotating planet. Yet they also show that Earth's environment is sensitive to geometry and solar input. Small long-term variations in orbit and axial orientation alter the distribution of sunlight over thousands of years and are known to influence ice ages and warmer intervals in the geological record. The planet therefore responds not only to daily weather and annual seasons, but also to slower changes in its orbital setting within the solar system. Seen from a distance, the oceans make Earth distinctive. Liquid water covers most of the surface, moderating temperature by storing and transporting heat. Ocean currents move energy from one region to another, linking tropics and poles. Winds drive surface motion, while differences in temperature and salinity influence deeper circulation. From the viewpoint of the wider solar system, this global ocean is both a result of Earth's position and a major factor in its stability. Too close to the Sun and long-term surface water would be threatened by heat. Too far and widespread freezing would dominate. Earth lies in a region where water can remain liquid at the surface under present atmospheric conditions. This balance is not guaranteed forever, nor is it controlled by distance alone, but it illustrates how planetary environment emerges from both solar input and local atmospheric properties. Earth's magnetic field adds another layer of response. Generated by motion in the liquid outer core, this field extends outward into space and forms a magnetosphere, a magnetic region that deflects much of the solar wind. Without this shield, the upper atmosphere would be more directly exposed to energetic charged particles. The magnetosphere is not rigid. It is compressed on the day side by the solar wind and stretched into a long tail on the night side. During periods of increased solar activity, such as coronal mass ejections or strong solar wind streams, the magnetosphere is disturbed more strongly. Charged particles can enter near the poles, producing auroras in the upper atmosphere. Instruments detect changes in radiation belts, magnetic currents, and atmospheric heating during such events. These responses show that Earth is linked to solar conditions in real time through invisible flows of plasma and magnetism. The upper atmosphere also responds directly to solar radiation, especially ultraviolet and X-ray energy. During periods of stronger solar activity, the upper layers can heat and expand slightly. This expansion increases drag on satellites in low Earth orbit, changing how quickly their paths decay unless corrected. The effect is small compared with the thickness of the whole atmosphere, but it is measurable and important for spacecraft operations. In this way, changes on the Sun can influence the practical environment around Earth, even when no visible change is noticed from the ground. The connection between Earth and the Sun is therefore not limited to light and warmth. It includes high-energy radiation, magnetic interaction, and particle flow. Material from space also continues to arrive. Tiny meteoroids enter the atmosphere constantly. Most burn up high above the surface, adding fine dust and metallic atoms to the upper air. Larger objects occasionally survive long enough to produce bright fireballs or reach the ground as meteorites. This steady input is modest compared with the mass of Earth, yet it reminds observers that Earth is not isolated from the matter moving through the solar system. Dust from comets and fragments from asteroids become part of the atmosphere for a time, linking the planet to the smaller bodies farther out. Earth also reflects sunlight and emits heat into space, participating in a continuous exchange of energy rather than existing as a sealed world. Cloud patterns visible from orbit reveal the speed and scale of atmospheric change. Storm systems move across oceans and continents. Tropical cyclones form over warm waters and weaken over cooler regions or land. Frontal systems wrap around areas of low pressure in middle latitudes. High clouds, low clouds, and broad bands of moisture shift from day to day. None of this is unusual by Earth standards, but from the perspective of planetary comparison, it shows a world in constant environmental motion. Unlike the thin hazes of Mars or the deep sulfuric clouds of Venus, Earth's clouds belong to a water cycle that operates across atmosphere, land, and sea. This cycle is driven by solar energy, and it shapes the visible face of the planet as much as continents or oceans do. Long-term observations also show that Earth's climate system changes over time due to both natural and human-driven factors. Variations in solar output across the ordinary solar cycle are measurable, but they are small compared with the present warming influence of increased greenhouse gases produced by human activity. Scientific observations indicate that recent global warming is driven primarily by these greenhouse gases, not by changes in the Sun. This distinction matters in a solar system context. Earth is influenced by solar variability, yet its present climate trend cannot be explained by solar change alone. The planet responds to many inputs at once, and the strongest present driver of long-term warming is within the atmosphere itself. This does not reduce the reality of solar effects on upper atmospheric conditions, space weather, and shorter-term variability. It simply places them in proper context. From afar, Earth seems balanced, luminous, and calm. Closer study shows a moving atmosphere, circulating oceans, a pulsing magnetic shield, and constant exchange with solar energy and interplanetary matter. It is a living member of the solar system in a physical sense, shaped by orbit, tilt, radiation, and magnetic connection. The evidence suggests that Earth remains stable enough to sustain long continuity. yet dynamic enough that subtle shifts in solar and planetary conditions can still be measured across its air and surrounding space. Beyond Earth's bright atmosphere and weather, the surrounding region opens into a quieter but more exposed domain. This is near-Earth space, where the planet's magnetic field, the solar wind, and the presence of the moon shape a local environment that is neither empty nor still. It is a region filled with charged particles, magnetic tension, radiation, drifting dust, and the faint traces of solar activity written into matter that has no air or flowing water to erase it. Earth moves through this region while the moon circles nearby, and together they form a system in which present conditions and ancient records exist side by side. New evidence suggests that this surrounding space, once treated mainly as a route for spacecraft, is better understood as an active layer of the solar system, where change is measured not only in storms of plasma, but in the silent accumulation of history on the lunar surface. Closest to Earth, the magnetic field dominates. It extends outward from the planet and forms a magnetosphere that deflects much of the solar wind. This protection is incomplete and dynamic. On the day side, where the solar wind presses most directly, the magnetic field is compressed. On the night side, it stretches far behind Earth into a long magnetic tail. Within this structure are regions of trapped particles known as the radiation belts. These belts contain energetic electrons and ions that spiral along magnetic field lines, bounce between northern and southern magnetic latitudes, and drift around the planet. Their intensity changes as solar activity varies. During disturbed conditions, particles are accelerated, redistributed, or temporarily lost. Instruments in orbit show that the belts can expand, contract, and shift in response to solar eruptions and fast streams of solar wind. Near-Earth space is therefore not a fixed shell. It is a changing electromagnetic environment. The solar wind supplies much of the energy that drives this activity. When conditions at the Sun are quiet, the interaction is moderate, and Earth's magnetic field holds a comparatively stable form. When the Sun releases bursts of plasma or stronger magnetic structure, the balance is disturbed. Energy is transferred into the magnetosphere. Magnetic field lines are stretched and reconnected, and particles are driven toward Earth's upper atmosphere. This process produces geomagnetic storms, which are periods of enhanced magnetic disturbance. During such storms, currents strengthen in near-Earth space and in the upper atmosphere. Auroras become brighter and spread farther from the poles than usual. Satellites encounter changing radiation conditions, and communication or navigation systems can be affected. These events show the direct link between the Sun and the space environment around Earth. Yet even during quiet intervals, near-Earth space remains active. The magnetosphere supports waves in plasma, which is gas whose atoms are ionized and electrically charged. These waves can scatter particles and influence where they move. The upper atmosphere releases atoms and ions into space from its outermost layers. The boundary between atmosphere and space is gradual rather than abrupt. Ultraviolet light from the Sun heats and ionizes the upper air, causing it to expand and contract depending on solar conditions. This means that the environment around Earth is partly terrestrial and partly solar, a blended frontier where the planet's own gases, magnetic field, and rotation meet the larger space weather system of the solar system. The Moon moves through this region without the protections Earth possesses. It has no dense atmosphere and no global magnetic field comparable to Earth's. Its surface is directly exposed to sunlight, solar wind particles, cosmic rays, and impacts from micrometeoroids. Because there is no weather, no rain, and no flowing water to remove evidence, the lunar surface preserves a long record of exposure. Dust grains in the regolith, which is the loose broken material covering the surface, are altered by radiation and impacts over immense spans of time. Tiny glassy particles form when impacts melt surface material. Solar wind ions become implanted in exposed grains. The result is a surface that acts as a quiet archive of the space environment. This archive is valuable because it preserves traces of both ordinary and unusual solar behavior. Samples returned from the Moon show that solar wind particles become embedded in lunar soil. By studying isotopes, which are forms of elements with different numbers of neutrons, and by examining damage trails left by energetic particles, scientists infer aspects of past solar activity and cosmic ray exposure. The lunar surface does not record these histories with perfect continuity. Because impacts churn the soil and mix layers over time, even so, it remains one of the clearest natural records of long-term space exposure available within reach of direct study. Observations indicate that some buried layers may preserve older surface conditions more cleanly than the constantly reworked topmost dust. It remains uncertain how completely each layer records the changing environment, but the Moon clearly retains evidence that Earth's atmosphere would erase. The Moon itself also influences near-Earth space. As it moves through Earth's magnetosphere and at other times outside it, the charging of its surface changes with surrounding plasma conditions. In sunlight, the lunar surface emits electrons and can become positively charged. In darkness, especially in a plasma-rich environment, it may accumulate negative charge. This affects how fine dust behaves near the surface. Though the extent of dust motion caused by electrical forces remains an area of ongoing study, the Moon also creates a wake in the solar wind, a region of disturbed flow behind it, because it lacks an atmosphere to gradually slow incoming particles. This wake reveals the direct interaction of a bare rocky body with the solar wind. The Moon is therefore not just a passive object orbiting Earth. It is a test surface, responding openly to the changing space environment. Near-Earth space contains additional matter as well. Dust from comets and asteroids passes through this region. Some grains intersect Earth's atmosphere and burn as meteors, while others strike the Moon directly, leaving tiny fresh scars. Because the Moon lacks air, even small impacts reach the ground. Over long periods, this steady bombardment contributes to the formation and overturning of the regolith. The lunar surface is not geologically active in the way Earth is, but it changes continuously through external exposure. Fresh craters form. Rocks break down through repeated heating and cooling and through impact shock. Radiation alters grain surfaces. The visible landscape remains ancient in broad outline, yet the fine scale is always being revised by the surrounding environment. For spacecraft and exploration, this region is especially important because it is where planetary shelter begins to give way to open exposure. Satellites in low orbit still pass through traces of the upper atmosphere and remain mostly within Earth's magnetic protection. Farther out, spacecraft encounter stronger radiation and more variable plasma conditions. Missions traveling to the Moon cross changing regions of Earth's magnetosphere and then enter a more direct solar environment. This journey through near-Earth space reveals a layered structure in which radiation, particle density, and magnetic influence all shift with distance and with solar activity. It is a local example of a larger solar system truth: the space between worlds is active, structured, and responsive. New evidence from lunar samples, orbiting instruments, and long-term monitoring of space weather suggests that the space around Earth and the surface of the Moon together form a record of connection. Earth's magnetic shield responds visibly to solar change. while the moon preserves the effects of long exposure with almost no shielding at all. One body is protected and dynamic, the other bare and preservative. Together they show how solar particles, radiation, and interplanetary dust continue to shape nearby space. This region is neither empty nor silent. It is a zone where present disturbance and ancient memory meet, held in the moving fields around Earth and in the dust of the moon. Venus moves closer to the Sun than Earth, bright in the sky and smooth in telescopic view, yet its brightness conceals one of the most severe planetary environments in the solar system. From afar, it appears calm because a continuous layer of cloud hides the surface below. That cloud cover reflects most incoming sunlight and gives Venus its pale, luminous appearance. Beneath it lies an atmosphere of extraordinary depth and pressure, composed mostly of carbon dioxide, with clouds of sulfuric acid suspended high above the ground. The planet turns slowly, far more slowly than Earth, and in the opposite direction to most planets. It has no global magnetic field like Earth's, and no ocean to moderate its climate. Even so, Venus is not a static world sealed beneath unchanging cloud. Its atmosphere circulates, its cloud patterns vary, its upper layers respond to solar activity, and its hidden surface shows signs that geological change may continue in the present age. The cloud deck of Venus forms the first visible region of its environment. These clouds lie high above the surface, where temperatures and pressures are less extreme than below, though still hostile by ordinary standards. They are made not of water droplets, but of sulfuric acid particles produced through chemical reactions involving sulfur compounds, sunlight, and the upper atmosphere. The cloud layers are thick and global, yet they are not uniform. Observations reveal bands, streaks, dark markings in ultraviolet light, and wave-like structures that move with the winds. These features show that the atmosphere is in constant motion. One of the most striking properties of Venus is superrotation, meaning that the atmosphere circles the planet much faster than the solid body rotates beneath it. While the planet itself takes longer than an Earth year to complete one turn, the upper clouds can circle the globe in only a few Earth days. This contrast reveals a deep separation between the motion of the atmosphere and the motion of the surface. The winds that drive this rapid circulation vary with altitude and latitude. Near the cloud tops, speeds are high and the movement is broad and persistent. Deeper down, the winds weaken, though the dense air still moves enough to transport heat and momentum. This circulation helps explain an important fact about Venus. Surface temperatures remain very high across most of the planet, with relatively small differences between day and night, or between equator and poles. The thick atmosphere redistributes heat efficiently. Combined with a strong greenhouse effect, this creates a planetary environment in which the lower atmosphere and surface remain intensely hot. The greenhouse effect occurs when certain gases absorb outgoing heat radiation and prevent it from escaping easily to space. On Venus, where carbon dioxide dominates and the atmosphere is massive, this effect is extreme. The heat at the surface is sufficient to melt lead, and the pressure is crushing, roughly comparable to that found deep in Earth's oceans. Yet even within this harsh stability, changes occur. The cloud tops show shifting wind speeds over time. Observations from orbiters and from Earth-based telescopes indicate that the speed of the upper atmosphere can vary over years and decades. Some patterns in the clouds appear and fade. Large stationary waves have been observed above highland regions, suggesting that air flowing over elevated terrain can influence the cloud structure far above. This is notable because the dense lower atmosphere and the high cloud deck are separated by many kilometers. Yet motion from the surface can still leave a trace aloft. Such observations show that Venus is not divided into isolated layers. Its atmosphere is vertically connected, with energy and motion passing between deep and high regions. The chemistry of the atmosphere also changes with altitude and sunlight. In the upper layers, solar radiation breaks apart molecules and drives reactions that produce sulfur-bearing compounds and affect the structure of the clouds. Trace gases, including sulfur dioxide and water vapor in very small amounts, vary in concentration. Some measurements suggest long-term changes in sulfur dioxide at high altitude, though interpretation is difficult because values depend on location, time, and instrument method. It remains uncertain how much of this variation reflects real atmospheric cycles and how much comes from the complexity of observing through such a dense and layered atmosphere. Even so, the evidence indicates that Venusian chemistry remains active, shaped by sunlight above and by possible inputs from lower atmospheric or volcanic sources below. Below the clouds, the middle and lower atmosphere become denser and hotter with descent. Visibility near the surface is limited by haze rather than thick cloud, and the light that reaches the ground is dim and orange. The air moves more slowly there, but because it is so dense, even moderate winds can exert force on fine particles and on the transfer of heat. The deep atmosphere turns the surface into part of a tightly coupled thermal system. Once heated, it changes only slowly. Day and night at ground level are therefore not sharply contrasted in temperature. Venus rotates so slowly that one might expect strong heating on the day side and cooling on the night side. Yet the atmosphere smooths those differences effectively. This is one of the clearest examples in the solar system of an atmosphere dominating the surface climate. The surface itself remains hidden from ordinary visible observation, but radar mapping has revealed mountains, broad volcanic plains, deformed crustal regions, and numerous volcanic structures. Much of Venus appears to have been resurfaced by volcanism in the geological past, covering older terrain with newer lava. The number of impact craters is lower than would be expected on an untouched ancient surface, indicating that large-scale resurfacing occurs after the early history of the planet. A major question has long remained whether Venus is geologically active today. Recent observations suggest that at least some volcanic activity may still occur. Changes detected in a volcanic vent between radar observations, together with measurements of atmospheric gases and surface heat patterns, are consistent with ongoing volcanism. It remains uncertain how widespread or frequent present eruptions are, but the possibility that Venus is still volcanically active has gained support from recent analysis. This possibility matters because it connects the hidden surface to the changing atmosphere above. Active volcanism could release sulfur dioxide and other gases into the atmosphere, influencing cloud chemistry and upper-level composition. The surface and air would then be linked not only through heat and topography, but also through continuing geological input. Venus may therefore be a planet where the consequences of deep internal heat still reach upward into the clouds, though in ways difficult to observe directly through the dense atmosphere. Venus also interacts with the Sun in a distinctive way because it lacks a strong intrinsic magnetic field. Instead of a broad internal magnetosphere like Earth's, it develops an induced magnetic region formed by the interaction of the solar wind with its upper atmosphere. Solar particles and ultraviolet radiation affect the ionosphere, the electrically charged upper layer, and contribute to atmospheric escape. Lighter atoms, especially hydrogen, can be lost to space over time. This process is one reason scientists infer that Venus likely loses large amounts of water long ago. Today, the planet is extremely dry. The loss of water and the growth of a dense carbon dioxide atmosphere are central parts of its climatic history, though the exact sequence remains under study. New evidence suggests that Venus should not be understood only as a static furnace beneath permanent clouds. Its atmosphere accelerates and varies, its chemistry responds to sunlight and perhaps to the ground below, and its surface may still be reshaped by internal activity. Behind the bright cloud cover lies a world of slow but persistent change, where deep heat, thick air, and solar influence remain in continuous interaction. Venus is hidden, but it is not still. Mercury circles closer to the Sun than any other planet, moving swiftly through intense light and strong gravitational pull. From a distance, it appears as a small rocky body, grey and heavily cratered, resembling the Moon in broad outline. Yet this resemblance hides a very different physical setting. Mercury lies deep within the Sun's influence. Daylight at its surface is far stronger than on Earth. The contrast between day and night is extreme because the planet has almost no atmosphere to store and move heat. Its year is short, but its rotation is slow, producing a strange rhythm in which the same landscape can endure long periods of blazing sunlight, followed by equally long intervals of darkness and cold. In this harsh environment, the surface, the thin envelope of atoms above it, and the small magnetic field of the planet all respond directly to nearness to the Sun. Mercury's surface is ancient in broad form. Large impact basins, overlapping craters, cliffs, and plains cover the planet, preserving a record of bombardment from the early solar system. But the surface is not only a fossil landscape, it continues to respond to present conditions. When the sun rises over a region after a long night, temperatures climb dramatically. Rocks and regolith, the loose broken surface material, expand under heat. When darkness returns, they contract again. Over many cycles, this repeated thermal stress can weaken rock and help break it down into finer debris. The process is slower and drier than weathering on Earth, yet it is real. Mercury's landscape changes not through rain, wind, or ice, but through sunlight, impact, and temperature extremes. The day side of Mercury becomes intensely hot, while the night side becomes extremely cold. Because the planet lacks a substantial atmosphere, there's almost no insulating blanket to soften this contrast. Heat absorbed by the ground during the day radiates back into space quickly after sunset. This makes Mercury one of the clearest examples of a world whose surface climate is controlled directly by exposure to sunlight rather than by atmospheric circulation. The intensity of solar heating also affects the uppermost grains of soil. Certain volatile elements, meaning substances that can be released more easily from surface materials, are influenced by repeated heating. At the same time, the surface is constantly struck by micrometeoroids, which vaporize tiny amounts of material on impact. These processes help supply the extremely thin exosphere, which is not a true atmosphere in the ordinary sense. The exosphere of Mercury consists of atoms that are so sparse they rarely collide with one another. They are released from the surface by several processes. One is photon-stimulated desorption, in which sunlight provides enough energy to knock atoms free from the surface. Another is sputtering, in which energetic particles from the solar wind strike the ground and eject atoms. Micrometeoroid impacts also blast material upward. Once released, these atoms follow ballistic paths, rise and fall, escape to space, or become ionized and swept away. Sodium, potassium, calcium, magnesium, and other species have been detected in this tenuous envelope. Observations indicate that the exosphere changes with location, time of day, and solar conditions. It is therefore not a stable shell around the planet. It is a constantly renewed and constantly lost population of atoms, closely tied to the surface below and to solar input above. Mercury's nearness to the Sun makes the solar wind especially important. The planet possesses a global magnetic field, but it is much weaker than Earth's. Even so, it is strong enough to carve out a small magnetosphere in the flow of solar particles. This magnetic region is compressed on the Sun-facing side and stretched behind the planet. Because Mercury is so close to the Sun, pressure from the solar wind is intense and highly variable, at times. The magnetosphere can be compressed so strongly that solar particles gain easier access to regions near the surface. Reconnection events, in which magnetic field lines break and join again, occur frequently and transfer energy into Mercury's local space environment. This creates a highly dynamic interaction between the planet and the Sun. The magnetic field itself is unusual. It is offset somewhat from the planet's center, which means the magnetic geometry differs between north and south. This asymmetry influences where charged particles can reach the surface and where material may be more efficiently removed into space. Observations from spacecraft indicate that ions originating from Mercury's surface can be accelerated in the magnetosphere and lost down the magnetic tail. In this way, the solar wind does not merely strike Mercury and pass on. It participates in a cycle of removal and redistribution, linking the exosphere, magnetic field, and surface composition. Mercury is therefore a planet where the boundary between ground and space is especially thin in a physical sense. Despite its closeness to the Sun, Mercury also holds a remarkable contrast at its poles. In permanently shadowed craters near the poles, sunlight never reaches the floor because of the planet's small axial tilt. These regions remain extremely cold, cold enough for water ice and other volatile substances to persist. Radar observations and spacecraft measurements strongly indicate the presence of ice deposits in some of these shadowed areas, protected beneath thin dark coverings in places. This creates one of the most striking juxtapositions in the solar system. A world whose equatorial day side is scorched by the Sun can still preserve frozen material in polar darkness. The existence of these deposits shows how local geometry can matter as much as general solar distance. It also suggests delivery of water-rich material by comets or volatile-rich asteroids, followed by long-term cold trapping. Mercury's surface also bears signs of internal change preserved in solid form. Long cliffs called lobate scarps cross parts of the planet. These are thought to form as Mercury cools and contracts internally over time, causing the crust to wrinkle and thrust over itself. This contraction likely operates over geological timescales rather than through rapid present-day motion. Yet it shows that the planet is not only shaped from outside, it has an internal history as well, one involving cooling. A large metallic core and the persistence of a magnetic field generated within that core. Mercury's large iron-rich core occupies a greater fraction of the planet than in Earth, Venus, or Mars. And this internal structure helps explain both its density and its magnetic behavior. Because Mercury lies so near the Sun, it is also a sensitive indicator of solar conditions. Variations in the solar wind, eruptions from the Sun, and changes in ultraviolet radiation all influence the planet more directly than they do farther out. The exosphere brightens or thins in different atomic species. Magnetic disturbances intensify. Surface sputtering rates change. Even fine dust near the planet may respond to the combined action of radiation, gravity, and electromagnetic forces. Though this remains an area of active study, new evidence from recent missions is refining knowledge of these interactions. showing that Mercury's environment is more dynamic and more chemically varied than older simple models suggest. Mercury in harsh light is therefore not merely a scorched stone turning silently near the Sun. It is a planet where sunlight fractures rock, where atoms are lifted from the surface and lost to space, where a small magnetic field struggles against a powerful solar wind, and where deep shadow preserves ancient ice. The evidence suggests that nearness itself is an engine of change. On Mercury, the pressure of the inner solar system is written directly onto the ground, the thin exosphere, and the magnetic space that surrounds the planet. Inside the orbits of the rocky planets, the solar system does not become empty. It grows finer, brighter, and in some ways more difficult to see. Between Mercury and the Sun, and throughout the broad region crossed by the inner planets, space contains a dispersed cloud of dust and tiny debris. These particles are far smaller than asteroids and usually much smaller than the grains of sand found on Earth. Yet together they form a meaningful component of the inner solar system. They reflect sunlight, absorb heat, re-radiate energy, and respond to gravity and radiation in ways that slowly reshape their paths. This is not a belt like the asteroid belt and not a set of distinct nuclei like comets. It is a distributed haze, continuously supplied and continuously reduced, made from the gradual breakdown of larger bodies and from the steady movement of material inward. In this crowded inner light, change is carried by particles so small that their collective presence is easier to detect than most individual grains. The most familiar sign of this dust cloud from Earth is the zodiacal light, a faint triangular glow that appears after sunset or before sunrise under dark skies, extending along the plane of the solar system. This glow is sunlight scattered by countless tiny particles orbiting the Sun. It reveals that the space between planets is not perfectly clear. The dust is concentrated toward the plane in which the planets move, because most of the material shares the broad geometry of solar system formation. Yet it does not remain fixed in one pattern. New dust is added by collisions among asteroids, by activity from comets, and by the slow erosion of small bodies. Old dust is altered, pushed, fragmented, or removed. The glow seen in the night sky is therefore not only a visual effect, it is evidence of ongoing renewal. One important source of inner solar system dust is the collision of rocky bodies. In the asteroid belt and among near-Earth objects, impacts break larger material into smaller fragments. Some collisions are catastrophic, reducing a parent body to many pieces. Others are less violent, chipping away at surfaces or producing showers of ejecta. Over time, repeated impacts grind fragments into ever finer particles. This process is often called a collisional cascade. It does not proceed smoothly or evenly, but over long periods it maintains a population of small debris. Some of that debris stays near its source region for a time. Some of it drifts inward, joining the more diffuse dust cloud closer to the Sun. In this way, the inner haze is partly fed by the slow destruction of rocky remnants farther out. Comets also contribute. As they move inward and heat increases, gas escapes from their nuclei and carries dust into space. Even after the bright coma and tail fade, the released particles continue to orbit the Sun. Some remain in trails close to the comet's orbit. Others spread more broadly under the influence of sunlight and planetary perturbations. Different sources therefore add particles with different sizes, compositions, and orbital properties. Some grains are more fragile. Some are richer in carbon-bearing material. Some are more silicate-rich, containing minerals common in rocky bodies. The inner dust cloud is not chemically uniform. It is a mixed population, shaped by the history of the bodies from which it comes and by the environmental forces that act on it afterward. Sunlight is one of the most important of those forces. It does more than illuminate the grains. When light strikes a dust particle, part of the energy is reflected, and part is absorbed and later emitted again as thermal radiation. For very small particles, the pressure of sunlight itself can significantly affect motion. In some cases, this radiation pressure can push particles onto more eccentric paths or even remove the very smallest grains from the solar system if they are light enough relative to their surface area. For somewhat larger grains, a subtler effect dominates over time. As a particle absorbs sunlight and re-radiates heat, the emitted radiation carries momentum. This causes the particle to lose a small amount of orbital energy and slowly spiral inward toward the Sun. This process is known as the Poynting-Robertson effect. It is gentle, but across long times it steadily draws dust inward from broader regions into the denser inner haze. Because of this inward drift, the inner solar system is not merely a place where dust happens to exist. It is a region through which material is being transported. A grain released by a collision in the asteroid belt or shed by a comet may spend long intervals circling the Sun while gradually moving inward. Along the way it may collide with another grain, fragment into smaller pieces, or become altered by heat and radiation. Some particles eventually fall into the Sun, some strike a planet, some are ejected after gravitational encounters. The dust cloud is therefore both a reservoir and a flow. It holds matter temporarily while also conveying it from one region to another. Closer to the Sun, conditions become harsher. Temperatures rise and some materials are no longer stable. Volatile coatings, if present, are lost. Grain surfaces can be modified by repeated heating, by solar ultraviolet radiation, and by bombardment from charged particles in the solar wind. Small particles may become electrically charged by photoelectric effects, in which sunlight causes electrons to be emitted, or by surrounding plasma. Once charged, they can respond in more complex ways to magnetic and electric conditions in near-solar space. The full behavior of dust very close to the Sun remains an area of active study, but observations indicate that the innermost regions contain structures and variations that are not explained by gravity alone. Even here, where the material is minute, the environment remains dynamic. The planets influence the dust as well. Their gravity can trap particles temporarily in resonant patterns, clear some regions, and perturb others. Earth and Venus, because of their sizes and positions, interact with portions of the inner dust cloud in ways that may create subtle enhancements or structures along certain orbital paths. These effects are delicate and often difficult to detect clearly, but they show that the planets do not simply move through an inert haze. They help shape it. Dust, in turn, enters planetary atmospheres. On Earth, some of it appears as meteoric material, burning in the upper air and adding metallic atoms to the atmosphere. On airless bodies such as Mercury or the Moon, small grains strike the surface directly and contribute to space weathering and regolith production. This dust also matters because it reflects the present state of the solar system's small body activity. A dust cloud cannot remain bright and populated forever without replenishment. Individual grains are removed by collisions, by inward drift, or by radiation forces. The continued presence of zodiacal dust means that new material is still being supplied. That supply comes from ongoing processes. Asteroids continue to collide, comets continue to shed matter, and small fragments continue to break apart. New evidence from observations and models suggests that the balance among these sources may vary over time and by location. It remains uncertain exactly what fraction of the inner dust cloud comes from each source at every size scale. But it is clear that the cloud is maintained by active replenishment rather than preserved unchanged from the earlier solar system. In the inner solar system, even the finest debris participates in the larger pattern of change. Dust drifts inward, light pushes it, heat alters it, planets shape it, and the sun ultimately removes much of it. This is a region where matter becomes increasingly broken down and redistributed, not through dramatic eruptions or giant impacts alone, but through countless subtle processes acting on tiny particles. The fading debris does not simply mark decay, it marks movement, renewal, and the continuing transfer of material toward the central star. In the crowded inner haze, the evidence of change is written in scattered light and in the slow inward fall of dust too small to see one by one. The inner dust fades into a more invisible medium, one that cannot be seen directly in ordinary light yet fills the solar system far more completely than any trail of debris. This is the solar wind, the continuous outward stream of charged particles released by the sun. It is made mainly of electrons and protons, with smaller amounts of heavier ions, and it carries with it the sun's magnetic field, stretched outward into interplanetary space. Though thin by terrestrial standards, the solar wind is the dominant moving substance in much of the space between planets. It shapes magnetospheres, sculpts comet tails, influences atmospheric escape, and helps define the outer boundary where the sun's domain meets the wider galaxy. It is not a constant flow in every detail. Its speed, density, temperature, and magnetic structure vary over time and with solar conditions. New evidence suggests that many of the changes seen across the solar system are linked, directly or indirectly, to this moving outward breath of the sun. The origin of the solar wind lies in the sun's outer atmosphere, the corona, where temperatures rise to extraordinary levels. In this hot environment, particles possess enough energy that the sun's gravity cannot hold them all indefinitely. Instead, gas expands outward. As it does, it becomes the solar wind. This expansion is not uniform. Some regions of the corona release faster streams, while others produce slower and denser flow, coronal holes, which are darker regions in certain wavelengths because they contain less dense hot gas, are often sources of faster solar wind. More complex magnetic regions on the sun tend to give rise to slower, more variable flow. As the sun rotates, these different streams sweep through the solar system in spiraling patterns because the source surface turns while the particles move outward. The result is not a simple radial wind, but a structured and rotating flow. The magnetic field carried outward by the solar wind forms what is often called the interplanetary magnetic field. Because of solar rotation, this field takes on a spiral shape rather than pointing straight outward. This geometry matters because charged particles move under magnetic influence, and because planets, dust, and smaller bodies interact with the solar wind partly through this carried field. A magnetic disturbance at the sun can thus be transported across planetary space and affect worlds far away. The field can also reverse direction across broad surfaces known as current sheets, where magnetic polarity changes. As planets move through these sectors of differing magnetic orientation, their local plasma environments respond. What appears to be empty space is therefore threaded by a rotating magnetic structure that changes with solar activity. The solar wind does not move at one constant speed. Fast streams can catch up with slower streams emitted earlier, producing compressed interaction regions where density and magnetic strength increase. These regions can travel outward across planetary orbits, carrying enhanced pressure and altered magnetic conditions. They are especially important because they can disturb planetary magnetospheres even when no explosive solar event occurs. During phases of greater solar activity, the Sun also releases more dramatic eruptions, including coronal mass ejections, which are large expulsions of magnetized plasma. When these travel through the solar system, they can strongly compress planetary magnetic fields, intensify auroras, disturb radiation belts, and increase atmospheric escape from unshielded worlds. The solar wind is therefore not only a background flow, it is also the carrier of shocks, compressions, and storms. At Mercury, the solar wind presses on a small magnetosphere and reaches close to the surface. At Venus and Mars, where there is no Earth-like global magnetic shield today, the solar wind interacts more directly with the upper atmosphere, helping remove ions to space over long times. At Earth, the solar wind energizes the magnetosphere and produces geomagnetic storms and auroras. At Jupiter and Saturn, the interaction is more complex because their magnetic fields are vast and their internal plasma sources, such as volcanic material from Io or icy plumes from Enceladus, also shape the system. Even in the distant outer solar system, the solar wind remains present. Though weaker and more spread out, it continues to interact with planets, moons, and comets, and it carries the changing influence of the Sun across immense distance. This common thread makes the solar wind one of the clearest mechanisms connecting the solar system into a single physical system. Comets show the effect with unusual clarity. When gas from a comet becomes ionized by sunlight, it is caught by the solar wind and swept into an ion tail pointing away from the Sun. Changes in solar wind direction and magnetic structure can alter this tail rapidly. In some cases, disturbances in the solar wind have caused a comet's ion tail to disconnect and reform. Such events show that the solar wind is not an abstract plasma flow observed only by instruments. It can visibly reshape matter released by small icy bodies. Dust is affected more by radiation pressure than by the solar wind directly, but even dust grains can become electrically charged and respond in subtle ways to the plasma environment. The wind of charged particles thus reaches into both the largest and smallest structures of the solar system. The solar wind also acts as a partial shield against some incoming cosmic rays from beyond the solar system. Its outward flow and carried magnetic field make it harder for many of these high-energy particles to travel inward. When solar activity is stronger and the solar wind more disturbed, the shielding effect tends to increase, reducing the cosmic ray intensity measured in the inner solar system. When solar activity is weaker, more cosmic rays can penetrate. This relationship has been observed over solar cycles, and even at the distant boundary of the heliosphere, the Sun's broad bubble of influence. The solar wind, therefore, does not only export solar conditions outward, it also helps regulate what enters from outside. Its properties change over the approximately 11-year solar activity cycle. During quieter intervals, the large-scale structure of the wind is often more ordered, with prominent fast streams from polar or extended coronal holes and fewer major eruptions. During more active intervals, the field becomes more tangled, the Sun releases more coronal mass ejections, and the distinction between fast and slow source regions can become more complex. Measurements from spacecraft near Earth and elsewhere show that solar wind density, temperature, speed, and magnetic variability all shift with this cycle. Yet not every change fits neatly into the ordinary pattern. Some cycles are stronger, some weaker, and some features persist or fade in ways that remain under study. New evidence suggests that recent solar behavior includes periods of unusually weak or unusually structured conditions compared with earlier cycles, though interpretation depends on the timescale chosen. Closer to the Sun, recent missions have begun sampling the solar wind before it has been fully mixed and smoothed by distance. These observations reveal fine magnetic structures, rapid reversals, and bursts of plasma behavior that were not previously seen so clearly. They show that the wind is born in a more irregular and textured state than older simplified models suggest. Some of this structure survives outward, while some merges into broader flow. This has deepened understanding of how the Sun's atmosphere releases particles and how magnetic energy is transferred into space. It remains uncertain which small-scale processes contribute most to heating the corona and accelerating different components of the wind, but the evidence clearly shows a more dynamic origin than once assumed. The solar wind environment is the moving medium through which all planets travel. It is invisible, but its effects are recorded in auroras, in stripped atmospheres, in bent comet tails, in compressed magnetic fields, and in the changing particle populations of space. It links the Sun to every region already crossed in this inward path. The evidence suggests that when something changes in the solar system, the solar wind is often part of the mechanism, carrying outward both the steady presence and the changing moods of the Sun. The solar wind arises from the Sun, but before it expands into interplanetary space, it begins at a visible threshold, the bright surface from which the Sun appears to shine. This visible layer is often called the photosphere, meaning the layer from which most of the Sun's light escapes into space. It is not a solid surface like the crust of a planet. It is a region in a vast ball of hot gas where the material becomes transparent enough for light to travel outward more freely. From far away, this layer appears smooth and steady, yet close observation reveals a changing face marked by fine cellular patterns, darker spots, brighter active regions, and shifting magnetic structures. New evidence suggests that this visible surface is one of the clearest places to see that the solar system's central star is not constant in detail, even while its total energy output remains comparatively stable on short timescales. At the broadest level, the solar surface glows because heat from deeper layers reaches it and escapes as radiation. The light is intense, and from Earth it dominates the sky, making subtler details impossible to see without instruments. When those details are resolved, the surface shows granulation, a fine mottled pattern of bright cells surrounded by darker boundaries. Each cell is the top of a convection flow, meaning a region where hot gas rises from below, cools as it radiates energy into space, and then sinks again at the edges. These granules are not fixed features. They form, change shape, and vanish over short intervals. The solar surface is therefore in constant small-scale motion, like a bright field of boiling light. This motion reflects the transport of energy upward from the deeper convective layers beneath. Above and within this shifting pattern appear darker structures known as sunspots. These are regions where magnetic fields rise through the visible surface and suppress convection, reducing the upward flow of heat. Because less heat reaches the surface there, sunspots appear darker than their surroundings, though they remain extremely hot in absolute terms. A sunspot often has a darker central region and a somewhat brighter outer structure of filaments. Sunspots can appear alone, but more often they occur in groups, associated with active magnetic regions. Their number changes over time in a cycle of rising and falling activity that averages about 11 years. During solar minimum, few spots may be visible. During solar maximum, many spots and active regions can appear across both hemispheres. This cycle is one of the most direct signs that the Sun changes over time in a regular but not perfectly identical pattern. The cycle is not simply a count of spots. The positions of sunspots also shift. At the beginning of a cycle, new spots tend to appear at higher solar latitudes. As the cycle progresses, spot formation gradually moves closer to the equator. This drifting pattern creates a well-known diagram when plotted over time, showing that the Sun's magnetic activity migrates systematically across the visible surface. The magnetic polarity of sunspot pairs also follows a cycle, reversing from one solar cycle to the next, so that the full magnetic cycle lasts about 22 years. Observations indicate that this magnetic reversal is a fundamental property of the Sun's dynamo, the process by which internal motion generates and reorganizes magnetic fields. The visible surface therefore records not just brightness changes, but the turning of a deep magnetic system. Around sunspots lie bright structures known as faculae, which are magnetic regions that appear especially bright near the solar limb or edge of the visible disk. These bright areas can partly offset the reduced brightness caused by sunspots. As a result, total solar output varies by only a small amount across the solar cycle, even though the visible face may look much more active during times of many spots. Measurements from spacecraft show that the Sun's total irradiance, meaning the total energy reaching a given area at Earth's distance, changes slightly with the cycle. The variation is real but modest. This matters because it shows that the Sun changes enough to influence the upper atmospheres of planets and the space environment, yet not enough to account for all long-term climate changes on Earth. The visible surface is active, but its changes are subtle in total energy compared with the dramatic appearance of individual features. Magnetic regions on the solar surface do more than darken or brighten local areas. They are often associated with flares and with the release of coronal mass ejections from higher layers of the solar atmosphere. A flare is a sudden release of magnetic energy that produces intense radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. These events are rooted in the rearrangement of magnetic fields that emerge through the visible surface and extend into the atmosphere above. Although the flare itself occurs mainly in higher layers, the underlying active region is visible on the surface through sunspots, bright magnetic concentrations, and changing fine structure. This makes the solar surface a map of where future energetic activity is more likely to arise. The visible surface also rotates, but not as a rigid body. Because the Sun is made of gas rather than solid rock, different latitudes rotate at different rates. The equatorial regions turn faster than the higher latitudes. This is known as differential rotation. It plays an important role in stretching and winding the Sun's magnetic field over time. On the surface, it can be tracked by following sunspots and other magnetic features as they move across the disk. Differential rotation means that magnetic patterns are gradually sheared, distorted, and reorganized. The visible face of the Sun is therefore not merely a passive expression of deep activity. It is also part of the mechanism through which magnetic complexity increases. High-resolution observations reveal still finer motions, magnetic flux, meaning bundles of magnetic field, constantly emerges on small scales and disperses again. Bright points flicker in magnetic lanes between granules. Tiny dark pores appear and vanish. Larger active regions grow, change shape, and decay over days or weeks. Filament channels and plage, which are bright magnetic areas, trace the organization of fields beyond individual spots. None of these features last forever. This solar surface is a place of continual appearance and disappearance, where magnetic energy rises from below, interacts with convective motion, and is then redistributed. This restless small-scale behavior is one reason why predicting solar activity remains difficult in detail, even when the broad cycle is understood. Long-term records of sunspot numbers, together with modern spacecraft observations, show that solar cycles differ from one another. Some are stronger, with more spots and more active regions. Some are weaker. There have been historical intervals, such as the Maunder minimum, during which very few sunspots are observed for decades. This does not mean the sun stops shining normally, but it does show that its magnetic expression can change substantially over longer timescales. Recent observations continue to refine understanding of cycle strength, hemispheric asymmetry, and the timing of peak activity. It remains uncertain exactly how deep internal processes determine the amplitude of a given cycle, but the surface provides the clearest visible evidence that the sun is not perfectly repetitive. The sun's visible surface is therefore a boundary between hidden depth and open space. It is where rising energy becomes light, where magnetic fields become visible as spots and bright regions, and where the changing state of the star can be observed directly. The evidence suggests that the face of the sun is never truly still. Granules boil and vanish, spots emerge and decay, latitudes rotate at different speeds, and magnetic patterns shift across years and decades. In this changing face of light, the central source of the solar system reveals that variation is not an exception. It is part of the ordinary behavior of the star around which everything else moves. Beneath the visible brightness of the sun lies a region that cannot be observed directly in ordinary light, yet its presence is written across every feature on the surface above. This is the convective layer, the outer part of the solar interior where energy is carried not mainly by radiation alone, but by the bulk motion of hot gas. In this region, matter rises, cools, and sinks again in an immense and continuous overturning. The sun is not solid, so these motions occur through plasma, which is gas-heated enough that electrons are no longer bound to atomic nuclei. The convective layer extends deeply below the visible surface and forms the hidden turning zone that gives rise to granulation, larger flow patterns, and much of the sun's magnetic behavior. New evidence suggests that understanding this region is essential for understanding why the solar system sometimes appears to change, because many outward variations begin here as organized motion beneath the light. The deeper one moves below the visible surface, the less transparent the sun becomes. Photons, which are particles of light, cannot travel freely there. They are absorbed and re-emitted many times, and energy transfer becomes slow if it depends on radiation alone. In the outer part of the sun, the temperature and density create conditions in which rising and sinking gas can move energy more efficiently. Hotter material from below becomes more buoyant, meaning it rises because it is slightly less dense than the cooler material above it. As it approaches the surface, it gives up energy, cools, and then descends again through darker lanes and broader returning flows. This overturning is convection. It operates on many scales at once. Small cells produce the granules seen at the surface. Larger cells and flow systems exist on scales much greater than the individual granules, though they are harder to map and interpret. These motions are not random in the simple sense. Rotation shapes them. Because the sun turns, rising and sinking flows are influenced by rotational forces that tend to organize motion differently at different latitudes and depths. The equatorial regions rotate faster than the polar regions, and this differential rotation is not limited to the visible surface. It extends through much of the convective layer. There are also meridional flows, which are slower circulations running roughly from equatorial regions toward the poles near the surface, and likely returning at depth. Together, convection, differential rotation, and these broader circulations help redistribute angular momentum, heat, and magnetic field. The Sun's outer interior is therefore not simply boiling in place. It is a structured flow system with patterns that evolve over time. One of the most important boundaries within this hidden region lies near the base of the convective layer, where the overlying turbulent convection meets the more stably stratified radiative region below. This transition zone is often called the tachocline. It is thought to be especially important because rotation changes rapidly across it, creating strong shear, meaning neighboring layers move at different speeds. Such shear can stretch and amplify magnetic fields. Many solar physicists regard this zone as a key part of the solar dynamo, the process that generates and renews the Sun's magnetic cycle. It remains uncertain exactly how magnetic fields are stored, intensified, and released in this region, but observations strongly support the idea that the interaction between differential rotation and convective motion plays a central role. The evidence for these hidden motions comes not from direct sight, but from heliosseismology, the study of waves that travel through the Sun. The solar surface rises and falls in countless small oscillations, caused by pressure waves trapped inside the star. By measuring how these waves move and how their frequencies vary, scientists infer conditions within the Sun, much as seismic waves on Earth reveal structures inside the planet. Heliosseismology shows that the Sun's interior rotates differentially in the outer layers and more uniformly deeper down. It reveals the depth of the convective layer and the existence of subsurface flow patterns. It also detects changes associated with the solar cycle, indicating that the hidden interior is not static. This method does not provide a perfect image, and some deeper flow details remain debated. But it offers the clearest evidence that the layers below the surface are active and changing. Convection also affects the emergence of magnetic flux. Magnetic fields generated or strengthened deeper down can become buoyant under certain conditions and rise through the convective layer in loops, where such loops break through the visible surface. Sunspots and active regions appear. The form they take at the surface depends in part on how they travel through the turbulent flows below. Some magnetic bundles emerge cleanly and strongly. Others are distorted, fragmented, or dispersed before reaching the surface. This means that the visible pattern of solar activity is shaped by subsurface weather of a kind, though it is magnetic and convective rather than atmospheric. The hidden turning layer does not merely feed energy upward. It also filters and organizes the magnetic structures that later affect the entire solar system. The scale of these motions is immense. A granule visible at the surface may last only minutes, but larger convective patterns can persist far longer. Supergranulation, a flow pattern larger than ordinary granules, organizes magnetic fields across broader areas of the surface. Even deeper giant cell motions may exist, though their exact properties remain harder to isolate clearly. The Sun's outer layers therefore contain nested systems of motion, from small and rapid to large and gradual. This hierarchy helps explain why solar activity can show both short-lived flickering behavior and slower coherent cycles. A brief bright point at the surface and a decade-long magnetic pattern may both ultimately depend on the same underlying convective engine, operating at different scales. Changes in the strength and pattern of convection may help explain why solar cycles are not all identical. Some cycles rise quickly and strongly, others are weaker or more prolonged. Hemispheres can differ in timing and intensity. The flows that transport magnetic field toward the poles and through the interior may vary from one cycle to another, altering how efficiently the magnetic system is renewed. Observations indicate that the Sun sometimes shows extended quiet periods and at other times heightened asymmetry between north and south. It remains uncertain which internal flow changes most strongly control these differences, but the evidence points toward the convective layer as a major participant. Variation in the hidden flows likely contributes to variation in the visible and outward-facing behavior of the Sun. This region also helps shape the energy that reaches the surface more generally. The Sun's luminosity, meaning its total power output, remains remarkably stable compared with the more dramatic appearances of spots and flares. Yet that stability is maintained by a vast and dynamic interior transport system. The convective layer smooths, mixes, and carries energy upward continuously. It is turbulent, but not chaotic in a way that destroys long-term balance. Instead, it supports a star that is both stable in total output and variable in local expression. This balance is one reason the solar system can remain broadly steady over billions of years, while still experiencing meaningful changes in magnetic and particle conditions over shorter timescales. Beneath the solar surface, then, lies not a quiet reservoir but a hidden turning world of rising heat, falling gas, rotational shear, and magnetic preparation. The evidence suggests that much of what later appears as spots, bright regions, solar wind structure, and changing space weather begins in these deep convective motions. The Sun's visible face tells only the upper part of the story. Below it, the layers continue to churn, organize, and reshape the magnetic patterns that connect the central star to every orbiting world. Deeper still, below the turning convective layer and beneath the region where radiation slowly diffuses outward, lies the central core of the Sun. This is the innermost region, the place where the solar system's energy begins. It cannot be seen directly. No spacecraft can approach it, no light emerges from it immediately, and no ordinary image can reveal its form. Yet every cloud on Venus, every dust grain drifting inward, every polar frost on Mars, every shifting boundary at the edge of the Sun's domain depends, in the longest sense, on the processes taking place here. The core is not a chamber of dramatic surface-like change. It is a region of immense pressure and temperature, where matter is compressed so strongly that atomic nuclei can overcome their electrical repulsion and join together. This joining is nuclear fusion, the process that converts hydrogen into helium and releases energy. New evidence does not suggest that the core is suddenly altered in any abrupt way. Instead, it clarifies how very slow deep processes and faster outer responses combine to create the impression that something in the solar system has changed. In the core, the Sun's mass presses inward from all sides. Gravity tries constantly to compress the star further. In response, the heat produced by fusion generates pressure that pushes outward. The Sun exists in balance between these opposing tendencies. This balance is called hydrostatic equilibrium. It is not a static stillness in the ordinary sense, but a sustained condition in which inward and outward forces match closely enough for the star to remain stable over vast timescales. The core is therefore the deepest source of continuity in the solar system. Without its long-term steadiness, the planets could not maintain their present environments over billions of years. Yet this steadiness does not mean perfect immobility. Fusion gradually changes the composition of the core. Hydrogen is consumed, helium accumulates, and the internal structure evolves, though on timescales far longer than any human history. The main fusion pathway in the Sun is the proton-proton chain. In this set of reactions, hydrogen nuclei ultimately combine to form helium, releasing energy in the form of gamma rays, neutrinos, and the kinetic energy of particles. The neutrinos are especially significant because they interact only very weakly with matter. They escape from the Sun almost immediately and travel outward into space, passing through planets and living bodies with almost no interruption. Measurements of solar neutrinos provide direct evidence that fusion is occurring in the core now. This is one of the rare ways in which the present state of the core can be observed almost in real time. Light, by contrast, takes a far longer and more complicated journey. A photon created in the core does not stream directly outward. It is repeatedly absorbed and re-emitted or scattered, taking an indirect path that can require immense spans of time before its energy reaches the surface and escapes into space. This long travel time matters because it means the Sun's visible surface does not respond instantly to conditions in the core. The energy seen as sunlight today reflects deep processes, but not in a direct moment-to-moment way. Shorter-term changes in the solar system, such as solar storms, sunspot cycles, variations in the solar wind, or changes in planetary space weather, are governed mainly by magnetic processes and outer solar layers, not by sudden fluctuations in core fusion. This distinction is essential. The core provides the long-term power supply. The outer layers shape how some of that power is expressed in magnetism, particle flow, and variable activity. When observations suggest that something in the solar system has changed, the cause usually lies not in a sudden alteration of fusion itself, but in the complex response of the Sun's outer regions and in the ways planets and small bodies react to them. Even so, the core is not irrelevant to change. Over millions and billions of years, its gradual evolution influences the entire solar system, as hydrogen is slowly converted into helium. The mean molecular weight in the core rises, and the core contracts slightly under gravity. This contraction increases temperature and pressure, which in turn affects the fusion rate. As a result, the Sun slowly becomes more luminous over geological time. Scientific models indicate that the young Sun is fainter in the distant past than it is now. This long brightening has consequences for planetary climates, surface water, atmospheric evolution, and habitability. Earth, Mars, and Venus all bear the marks of this deep temporal influence. The change is not sudden, but it is real. The solar system of the far past is lit by a somewhat dimmer sun than the one shining today. Heliosismology and neutrino measurements together provide the strongest evidence for the present understanding of the core. Heliosismology constrains the interior structure by analyzing pressure waves that pass through the Sun. Neutrino detectors confirm the nuclear reactions expected from stellar theory. Together they show that the core behaves in line with the broader consensus of stellar physics. It remains uncertain whether there are subtle internal motions, compositional gradients, or mixing processes not yet fully characterized. But these uncertainties do not overturn the main picture. The Sun is a stable main sequence star, slowly converting hydrogen to helium in its core and supplying the energy that sustains the broader solar system environment. The deeper lesson of the core is one of timescale. Some changes in the solar system occur over minutes or hours, such as flares, auroras, or shifting comet tails. Some unfold across years and decades, such as solar cycles, atmospheric variations on planets, or movements in the heliospheric boundary. Others stretch across millions or billions of years, including planetary cooling, atmospheric loss, orbital evolution, and the gradual brightening of the Sun. These layers of time coexist. A modern observer may notice new evidence and conclude that something has changed. In one sense, that conclusion is correct, because the solar system is always changing at some level. In another sense, The deepest source remains extraordinarily stable, changing so slowly that the continuity of the whole system depends on it. The impression of sudden transformation often emerges when better instruments reveal processes that have been active all along, or when ordinary cycles reach a visible phase. This distinction between deep stability and outer variability helps unify everything observed along the path from the solar system's edge inward. The shifting heliosphere responds to solar output and interstellar conditions. Distant icy bodies preserve orbital histories and subtle seasonal changes. Giant planets show storms, rings, and magnetic interactions. Comets release gas and dust as they move inward. Asteroids drift, weather, and collide. Mars breathes through seasonal carbon dioxide exchange. Earth responds through atmosphere and magnetosphere. Venus hides active circulation and perhaps ongoing volcanism. Mercury endures direct solar pressure. Inner dust migrates under light. The solar wind carries change outward. The visible surface of the sun displays spots and bright regions. Beneath it, convection and rotation shape magnetic cycles. At the center, fusion proceeds with profound steadiness, slowly altering the star over time so long that all shorter patterns unfold within that deeper continuity. New evidence, then, suggests not that the solar system has entered a wholly different state, but that change is one of its basic conditions. What has changed most clearly is the ability to detect fine motion, long cycles, and hidden connections. Observations indicate a system in which the outer signs of variation are real, sometimes surprising and worthy of careful study, while the central engine remains stable enough to sustain them. The solar system is not a machine frozen into permanence. It is a layered process, with a quiet core and responsive outer regions. At the deepest source, the truth is not sudden upheaval, but ongoing transformation held within enduring balance. The solar system settles, in the mind, into a quieter form. The outer boundary continues to breathe against the faint pressure between the stars. Far icy bodies continue their long circuits in cold light. Giant planets continue to turn beneath storms and rings. Dust continues to drift inward. Small stones continue to collide, to fracture, and to wander. Mars continues its thin seasonal exchange of frost, air, and dust. Earth continues to move within light, water, cloud, and magnetic shelter. The Moon continues to keep its silent record in exposed dust. Venus continues beneath its high bright cloud, and Mercury continues in hard alternation between brilliance and shadow. Closer to the Sun, the finer haze of particles remains in motion, slowly falling inward through the pressure of light and time. The solar wind continues to spread through all the regions already crossed, carrying magnetic structure outward across the dark. The visible face of the Sun continues to change in small details, brightening here, dimming there, producing spots, faculae, waves, and shifting fields. Beneath that light, the deeper layers continue their immense overturning, rising and sinking in a hidden rhythm. Deeper still, in the core, fusion continues with the patience of stellar time, almost unchanged from day to day, yet never wholly still across the longest ages. Nothing in this system stands outside change, yet not every change is sudden, and not every change is a warning. Much of what appears new is part of a pattern already underway, seen more clearly now through longer watching and better instruments. The solar system remains vast, connected, and active, shaped by deep stability and by ceaseless surface response. In that balance, the planets continue their paths, the Sun continues its work, and the long order of motion carries on through the dark. Quite space between worlds.